Hi all, welcome to a new video lecture on the course Algorithm Analysis and Design. So here we will be discussing something like the notion of efficiency. So in the previous video lectures on this course we discussed what is basically an algorithm and what are all the characteristics of the algorithm and some fundamental things like what are different types of algorithm like iterative, recursive algorithm. So such terminologies we gone through, right? So now it's a time for us to explore more into the top concept called efficiency. So let me tell you, so we already seen like if I have a computational problem say P, there are different ways to solve it, right? So A1 maybe approach 1 or algorithm 1, A2 is another way of doing the same one. Like that one can think about some k number of ways, and we will always try to improve from one way to another, right? So whenever someone come up with this algorithm A1 say with some time concept, like if it is taking this much time, now naturally the question is like shall I improve it, right? So there may be some small modifications such that this A2 may be performing better than this A1. So like that we will keep on adding improvement, and finally at some point we may stop and saying that this is the best ever algorithm possible and we can't proceed further. So that is a basic idea. Now the question is some if one person is coming up with approach 1, another one is coming with the approach 2, it's not developing systematically, right? So many people will be trying at a given problem at the same time at different places and all. So finally whenever this problem is coming as a competition problem to a new person, so he should be able to choose among this A1, A2, etc, AK, right? So which is good. So that is a task we are having. So the question is how to compare this algorithm, right? How to compare these algorithms. So definitely we will be looking at the time taken or time complexity analysis and space complexity analysis. Actually what we are looking at is how much resources the algorithm is supposed to take. Okay, so the main resource is of course the time, right? The CPU time or the system time. So that is one way, or in some general platform independent way of analyzing the time. And what about the space taken by the algorithm, say in the primary memory or in the secondary memory? So fine, whenever there is a tie, say with respect to time, you can think about space like that. Okay, so normally the notion is time complexity analysis and space complexity also. Typically we use space complexity analysis when there is a tie with respect to time, but anyway we should be able to know how to do analyze both. Okay, so typically time, what is coming into your mind is the CPU time taken, right? The actual system time taken. Is it so? So that is a question. So when it comes to time complexity analysis, is it system time that we are thinking about? So let's see what is the problem if we are focusing on system time. What we can do is let's fix some architecture. You can fix anything, say I'm fixing this Intel i5 architecture or something. So now what I'm doing is this algorithm 1 I'm taking, and I'm manually calculating, say, or using some tool I'm calculating the average execution time of this algorithm A1 on a given input I1, I2, etc, Ik, and then I am taking average over all this value. Okay, so I run this algorithm A1 on a input instance I1, then I note that down the actual system time taken by the algorithm. Okay, so that you can do. Then I run the same algorithm on a different input instance I2, and I noted down the time. So like that some so the number of algorithms are also k here also. So some you can use a different variable, some m set of input instances I taken. Okay, so if you increase the value of this m, if you are taking more and more instances, you will be getting a very good average, right? So that's up to you. So some set of input instances you are taking and you are running your algorithm and you are noting down the system time, and then you are taking the average. So the same procedure you are doing for this A2 also. So you are taking average of the execution time on input instances I1, I2, etc, Im, say m number of instances are there, and finally you can do the same for AK. So what I can say that it is not giving you the exact time, some approximate time you are getting. Okay, so that's enough. Now what you can do, you can simply find out the minimum, right? So what is the minimum out of these two? Suppose the minimum is given by algorithm say A3, then I can say that A3 is the best. Now you have to mention one more thing with respect to the particular architecture you chosen, with respect to this so some sample architecture you chosen, right, with respect to this one. Now the question is, if I am taking a different architecture, say some AMD Athlon or something, shall I get the same analysis, right? So the same way there also you can note down the time taken by this A1, A2, etc., AK. And when you are taking the minimum of all this, what is the guarantee that it is also going to give you A3? So there is no guarantee. It may give you a different algorithm. It may choose a different algorithm, say A2 as the best one, or some other algorithm as the best one. Then this architecture may say that A2 is the best. So see the difficulty we are facing. So now this is with respect to this particular architecture I mentioned. Okay, something randomly I am choosing, so it's not specific to anything. Now you may be wondering why this is choosing someone different, because it's a different architecture. Definitely the same algorithm, different, I mean, if you are looking at the basic operations and all, some comparisons, addition, incrementation, many things will be there. So one architecture may be good in doing this comparison well, right? The other architecture may be doing this addition say with less time than this comparison. I'm just telling. So the actual time taken by different architecture for basic operation, it may vary. So accordingly the time calculated by it for different input instances, and the average of course will vary. So chances are there that this different architecture is giving you a different running time. Okay, so what is the highlight here? And let me tell you one more thing. So that is one point. Now suppose you fix a single architecture. Okay, so it's like a even so we are not trying to experiment with the different architecture. Even if we say fix one architecture, let me tell you a different problem. It is like the algorithm you are running, say one particular algorithm you are running at say 10 a.m. It may be showing you a time, some 10 microseconds something. The same algorithm you are executing at some some 5 p.m. Like that, it may give you some, I mean, it may take more time like that. So or some 7 p.m. it may be even more worst. Okay, so what is happening here? Why this differences in time for the same algorithm when you are executing at different time, right? Timeline. So it's because of the traffic, of course. So some background process will be running, right? Some background processes may contribute to this difference in timing, something like that. Okay, difference in timing. So what I was telling is on a conclusion, the analysis which is where you are calculating system time. Okay, so the analysis based on the system time may vary with respect to the architecture we are using, and also with respect to the time of execution of the program, something like that. Many parameters will affect. So what we need in a conclusion, what we can say is we need a platform independent analysis. That is our purpose. Okay, so can we do this? So some architecturally neutral way of analyzing things. So that is what we are looking at. Okay, so hope you get an idea about. So if the analysis is something that depends on the underlying architecture, or if the running time is varying over time, so these things are something that we don't want, right? So whenever I am saying that this algorithm is better than this. I need a general way of answering it. Okay, so some general way should be there. It should not depend on the time on which I run this algorithm, or it should not depend on the architecture where I run this algorithm. So that about it. I tried to take some simple example to show you like what is the difficulty when one is having a platform dependent analysis. Now this is something I taken from the textbook, a slightly different example also. I don't know at this point whether you can follow this example, but anyway I'm taking it. Some after some time means once we analyze sorting algorithms and all, you will get an idea like why this running time. So right now I'm just trying to explain. So if you are not able to follow, okay, leave it. You can come after some time. Okay. Anyway, let's see. So here they are considering say two algorithms as a for a comparison point of view. The one is insertion sort algorithm and another one is a merge sort algorithm. I think in data structure classes you already know how these algorithms are working, and you have a minimum idea about this running time, something like 2 times n square. Okay, or you may be knowing this something like this order of n square. Typically I got like a 2 into n square running time, which typically we ignore this constant, and the reason why this notation, what is the meaning why these constants are being ignored, those things we will see very soon. Okay, anyway, at this point I feel like you on data structure classes you just have an idea about the analysis, something like this. The birth sort is taking some n log n time, so that understanding you may be having, otherwise you can leave it, no problem. Okay, so if that is the case, so what they're trying to say, insertion sort is on way of sorting a given set of element, and it is taking some running time like 2 times n square. Some n may be to sort n number of elements. Okay, so n is the size of the array, so we know that this is a time taken. And for merge sort, someone already analyzed the algorithm and he come up with the, so how to analyze that we will see. Okay, he is giving you the value like it is taking some 50 n log n time. Okay, now let me ask you the question, which algorithm is better? At this point can you answer me, like which algorithm is better? So the one algorithm is taking on an average, we just ignore that constant, so we can focus on constant also. But as of now I am trying to convince you with this n square and n log n, which is smaller quantity. So that is what I want to tell you. But anyway, we have a separate session of videos on this where we will exactly see how this which is bigger and also that analysis way. But anyway, now you have a rough idea like what is n square. It is like n into n, so here it is n log n, so you can cancel this n and n, both are same. Now the question is whether this n or log n, which is large. Okay, and I think you know at this point by default if I am writing log n, it means logarithm to the base 2. Okay, because we are talking about computers and running time of an algorithm in a computer, so base you have to assume like a 2. Okay, and again more details about this base we will see. Anyway, this is what is, so here also if they are writing like this, so this LG is actually in your textbook, this notation they are using LG. LG by default it means logarithm to the base 2. Okay, so if I am writing something like a logarithm of x, LGX means logarithm to the base 2 for x. Okay, so that is a default meaning. Anyway, now can you tell me if that is the case which is large, whenever I have a number, so suppose I am taking this n is equal to 1024. Okay, if n is equal to 1024, so this side what you are getting is just I am taking a value 1024 to the base 2, and what is this logarithm of 1024 is actually 2 raised to 10. Okay, to the base 2. Now what is log a power n? Log a power n is n log a. Hope you remember this formula from your mathematical classes, because so this logarithm we will see at many points. Log a power n to any base x is given by n log a to that base. So this is a property of logarithm. Okay, so these are all you can remember like different points. Okay, this is one thing I am telling you now. If you are not able to remember it, this is something you studied in your smaller classes. So this notation may be new to you. In Corman textbook they are following this notation for logarithm to the base 2, and at the beginning they are telling also something like a natural log you denote like this, right? So like that notation. Now tell me what is this value. This is 10 only, right? So because log 2 to the base 2 is 1. So again, if somebody don't know that, log x to the base x is always 1. Okay, so this is again a property from logarithm. So at this point, when this n is 1024, log n is just 10, right? So this is very very large compared to this. So when you're taking logarithm of something, you will get a very very small value. See, 10 and 1024, it is some 100 times more, right? So that difference is there. By example, you convinced, but there are formal ways of convincing this also. Anyway, so at this point, if that is the case, finally this n square will be bigger quantity than n log n. So can you tell me, so who is this n square running time? It is your insertion sort, right? Insertion sort, and this is your merge sort. Now for a given problem, whether you will prefer merge sort or insertion sort, definitely you will go with the merge sort, because merge sort is taking less time. Okay, so that you are convinced. Hope you understood it. Now, what they are trying to say is, so to conclude this, to analyze this, the trivial method we try to follow, like the actual running time of the algorithm, say in seconds or in hours, that we try to note down. Okay. Now, for that, what we done is, like we have a faster computer. So computer A is faster. Okay. That is running this insertion sort. So by default this insertion sort is taking n square, I mean more time, but still we try to execute this insertion sort using a faster machine. Okay, so the architecture is now very good, but algorithm is poor. So that is what we are trying to say. So using a faster computer, we run the insertion sort against a slower computer, that is B, where we executed merge sort. So merge sort we executed on so on a lower speed computer, that is B, and the insertion sort we executed on a faster computer, that is A. Okay, so hope these things are in your brain. And now at this point you can tell me what about the, so B is lower, right? So B can execute only 10 million instructions per second. So this hope you know this terminology from your microprocessors, computer organization classes, like MIPS architecture. What does it mean? In every second, this one is capable of executing 10 million. Okay, so that's a very large number. But your this is about architecture B, but architecture A is basically much more faster. So it can execute 10 billion instructions per second. Okay, so A is faster in the sense it is able to execute 10 billion, and billion and million is 10 lakhs around. This is 10 crore, right? So it is around 1,000 times faster. So that kind of a supercomputer we are having as A, and using that we are executing our slower algorithm, that is insertion sort. Okay, so that is the conclusion. Now using a slower or algorithm, computer, say B, we are executing a faster algorithm, that is merge sort. Now let's see what about the running time. So suppose the number of elements to be sorted, that is your n, right? So they are taking like n is equal to 10 million. 10 million. What is million? It is 10 raised to 6, I think, right? So 10 lakhs, that is 1 million. Yeah, 10 million numbers I have. So this many numbers I am supposed to sort. Okay, so that is my target. And two approaches I am having. The first approach is insertion sort. Okay, so what is running time of insertion sort? It is given like it is 2n square. Okay, 2n square. So this is the running time of insertion sort as given. 2 into what is your n? N is 10 into 10 power 6. So 10 into 10 power 6 is 10 power 7. Okay, so the algorithm will be taking 2n square time. So n is 10 power 7, 2 into n square. Okay, so this much time the algorithm will be taking. I mean this many instructions it has to execute. Sorry, so the total number of instructions executed by insertion sort for an array of size n is 2n square, where merge sort is going to execute 50 n log n instructions. Okay, so when it comes to 2n square instruction, what we are having is we are executing it over say machine A, and the speed of machine A is it is faster, right? 10 billion instruction per second. So in every second it can execute. So if you are looking at machine A, what it is do in every second, it can do 10 billion. So what is 10 billion? 10 into 1 billion is 10 power 9, right? So it is some 1,000 times more than this million. Anyway, 10 power 9 instructions are executed per second. Then what is the time taken to execute one instruction? one instruction will be executed in every one by this value. So this is around 10 raised to 10. Okay, so this much time, 1 by 10 power 10 seconds is needed for um, one instruction. If that is the case, how many instructions I am having for the insertion sort algorithm? 2n square instruction. So 2 into n square, this many instructions will be taking 2n square multiplied by 1 by 10 raised to 10. Okay, so this is the total time it is taking for the insertion sort algorithm. So when you calculate this, you can use calculator and you can see that this is around this much seconds. So when you convert it to hours, it is something more than 5.5 hours. Okay, so keep that in mind. Now this is about the execution of insertion sort, a slower approach for so this is your okay, so this is slower, right? It's taking more time approach for sorting algorithm, but we executed it in a faster machine. Okay, now merge sort, you know, algorithm wise it is the smart one, but the machine you used is slower, like it is some 1000 times slower than the other one. And you know, the second machine, I mean machine B is slower, and it can do 10 million instruction per second, right? So in every second, so I am talking about machine B. So here I am talking about machine A. Okay, so this is the performance of machine A. Now we are looking at the performance of machine B. In every 1 second it can do 10 million, that is, so this many instructions it can handle. Okay, now if that is the case, in one instruction will be executed in 1 by 10 raised to 7, 10 into 10, so this many second. If that is the case, how many instruction I have to execute? Because I am running merge sort algorithm and I find that for an array of size n, the algorithm is taking some 50 n log n instructions. So 50 into n is 10. Already we know the array size is some 10 raised to 7, right? So this is our input size. So 10 raised to 7 into logarithm of 10 raised to 7, or logarithm to the base 2. So this many instruction will be taking that divided by 10 raised to 7. Okay, so just like before you can calculate. And now this is something a smaller value. It is only 20 minutes. Okay, it's less than 20 minutes only. So what is the conclusion? So while when you run this insertion sort and merge sort, say parallelly on machine A and machine B, you saw that the merge sort is taking less than 20 minutes of time, where the insertion sort is taking more than 5.5 hours of time. Yes, that about it. So what we are trying to say by this example is, maybe you might feel this as many technical things are coming, like this, what is this n log and n square. So you can leave it for the time being, no problem. From the textbook I just taken on example, that's all. So what we are trying to say is like this power of this merge sort, right? So actually we executed this merge sort algorithm on a very poor performing algorithm. So I mean machine architecture is something like a very poor, but still means independent of the architecture, the algorithm is giving you a very good running time. Let's see, even though you executed insertion sort in a very faster machine, it still taken 5.5 hours. So that feel I want to give you, like, so that is the power of different algorithm. So if I'm saying that I got an algorithm which is running in n square time, someone else come with n log n time, you have to appreciate it. So it's like this n log n, this reduction is not that much easy. Anyway, this so I don't think so whether this example at this point is correct or not, but anyway, the thing is that even though I used a very slow machine, the merge sort algorithm taken some, I mean, it's just taken hardly, I mean, less than 20 minutes of time only, where this insertion sort, even though I used a very good performing machine, it took some 5.5 hours. So that shows how this, I mean, the notion of efficiency, so which is better. So the importance of finding an algorithm, so that is that perform better than the other one. Okay, so if you stop your what I can tell. So once you get this insertion sort algorithm, someone developed it. If people stop thinking about a better algorithm, you will not get this kind of an efficiency. So here I taken an array which is of some 10 power 7 elements, okay, or some 10 million elements. The this difference will be much higher if you are taking some 100 million element, okay. So as the number of elements grows more and more, this difference in execution time, that matters a lot. Even though you are getting a small reduction in running time, that matters a lot, okay. So I hope you get a feel about it. So that about the efficiency notion. So why we want to find something better than the other one, okay. And sometimes if you keep on going like that, at some point you are forced to stop, like you can't proceed, in the sense uh, there may not be any other way to find a better algorithm. So that also you can formally prove by something like a lower bound theory, some mathematical, using some sophisticated mathematical arguments, you can prove that. So this about the importance. So I just taken this example, that's all. Otherwise you just be at this point. So what we are discussing here is how to find out the better algorithm, so that way. So what is the relevance of that is what we seen with the example I discussed so far, okay. And the concluding, we need a platform independent analysis, and we are going to see how this platform independent analysis can be done. So let's start with some fundamental things. So when you analyze an algorithm, has come to mean predicting the resources. So basically we are trying to find out how much resources we are taking, like in terms of time and space and other things. Occasionally resources such as memory. And when it comes to some network protocol, network algorithms, we will look at this communication bandwidth or the computer hardware used, which are of primary concern, but most often it is computational time it taken, okay. So that matters. That is what we are interested to measure. And when there is a tie with respect to time, we can go for other ways of analyzing the algorithm. Generally, by analyzing the algorithm, analyzing several candidate algorithm for a problem, we can identify the most efficient one. Like out of that merge and insertion, we find out like a merge is much better than that, okay. Even though you are using a very poor performing computer, this merge will give you a good performance, okay. So that is the overall goals, to identify the best, okay. So now how we can do that? So we need a model of implementation that is independent of the actual hardware we are having. So this is typically called as a RAM model of computation. In the textbook throughout they are using this kind of a model, or in general also for analyzing this kind of a model is basically people are assuming, okay. And it is something very simple. It's a very fundamental model. In RAM model, the instructions are executed one after another with no concurrent operation. So here we are not thinking about the parallel execution, nothing. Normal sequential execution is what we are focusing, and how to analyze things out of it, okay. So the sequential flow we are maintaining in RAM model. It's a very simple basic model, and it contains instructions commonly found in any real computer, like arithmetic operations, add, subtract, multiply, divide, remainder, floor, seal, and of course some logical operations also you can consider. Mainly these things are given in textbook, and data movement and control instructions. So these are all fundamental instruction that you can see in your in any programming language and implementation, right? So we must be careful not to abuse the RAM model. Just like what they mean is, we are saying that there is a single instruction for sort, okay. So simply by calling it you can sort the element, but that is not correct, right? So that is not a genuine way of doing it. We are supposed to measure. So when you are sorting it, some set of comparison, so you go for the fundamental operation like a comparison, arithmetic, etc., and count them, and accordingly you would come up with the running time. Don't say like it is just involving just a sort function call and is taking constant time. It is not like that. Inside that sort, with respect to the size of the input array which is to be sorted, it will take a different running time. So that you have to find out. Then we could sort in just one instruction. That is what we don't want. Such a RAM would be unrealistic. So what we need is a realistic model of computation. Okay, so now when it comes to analysis, one thing that you have to keep in mind is the input size. So always we try to express the running time of an algorithm as a function of the input size, like what we seen for the insertion and merge sort. N is the size of the array we are giving as input to the algorithm. So with I have an array with a 10 element or 25 element, what is the time taken? So like that I will be analyzing. So in general, the size of the input, right? The time taken by an algorithm, we express as a function. So it grows with the size of the input. So it is traditional to describe the running time of an algorithm as a function of the input size. So like that is O of that meaning of the function we will see soon. The best notion for the input size depends on the problem being studied. Yeah, that is one thing. Most of the algorithm like the searching or sorting, right? The array based algorithm and all, the array size can be taken as the size of the input, because that array of elements is our input, right? So the size you can measure like that. But suppose suppose you are having a number theoretic algorithm where you are just having a single number, for example, so given a number n, check for prime, right? Check for prime, whether it is prime or not, you know the algorithm. So now the input is just a single number or GCD of two numbers, or what is given here, the okay. So this is here they are talking about the array size. Okay, so now if it is like a multiplication of two integers, you can see that the size of the array, and all here there is no array involved, just a single number or one or two numbers. So what you can do is you can take this number of bits required to represent that number in computer memory, the binary bits taken as a measure for analyzing the algorithm. Okay, so that is one thing. Now if it is a graph theoretic algorithm, like where the input is a certain graph and you have to analyze the algorithm, what you can see, the input you can take like the number of vertices and edges of the graph. Okay, so that you can with respect to how many edges and vertices are there in the graph, accordingly you can express the running time. Okay, so that also we will see how to analyze the searching BFS and some other shortest path algorithms and all. Okay, so now this is the final thing. We are doing something called as a step count analysis. Okay, so where the running time of an algorithm on a particular input is expressed as a function of the number of primitive operations or steps involved. Okay, so how many primitives or basic operations are involved? Basic operations are nothing but those listed here, some basic fundamental operations supported by the computer, right? It can be addition, subtraction, comparison, data movement, or anything. So what is the dominant operation that we will focus? So it is convenient to define the notion of step so that it is machine independent as possible. So try to express it independent of the machine. So for the moment, let us adopt the following view, like one line is taking some constant amount of time, and how many lines are there, so like that. So that is one way of analyzing, and if you want you can go a little bit deeper also. We will see this one. Okay, and we will assume this is the cost of this particular line, so that what is the total cost. Okay, so n lines are involved, or if it is in a loop, it is executed some n times. So the time for execution of a single iteration is say ci, then what is the total time? So that is the way we are analyzing the algorithm as a whole. Now let me just ask you a question. So what we seen is the step count analysis, right? Step count analysis. And basically what is step count? So what is step count? So it is the count or the frequency of fundamental operations, right? Fundamental operations involved in any algorithm. Okay, or the fundamental operations are otherwise called primitive operations, or simply the prime operations. You can use any terminology. Okay, so that about it. For a given computational model like a RAM model, you can count it and you can say that this is the running time. So this is basically what we are doing. Now the question is it a good metric? Good metric. So when you can say that a particular measure is good in the sense it should be close to the reality, right? So are we close to Reality means the actual implementation. So if you are far away from the actual implementation and you are saying that this is the total running time of the algorithm in a general way, that is not good, right? So are we close to the reality? So that is something you can think about. So what is reality in case of this one? So what is coming into our mind is what we need is the actual system time. So is it close to that reality? In the sense reality here, we talk about system time, right? So are we getting something closer to the actual system time, but still it is not specific to a given architecture? Is that the case? So like that we can ask. So definitely, if you are asking like that, the answer is yes. I will just give you a feel like why the answer is yes. For example, suppose you saw that in a given architecture, the number of comparisons are found to be some n, where n is say the input size, and that many comparisons are involved in the architecture, something like that. Okay, now you know that in that particular architecture, one comparison is taking some say some 4 clock cycles, something like that, you know, the CPU clock cycles. And now you can calculate the system time, right, for doing this. So time will be now n into 4 into clock time. So if you are doing like that, you will get the actual execution system time of this particular algorithm, say in some units, like in some seconds or something, you will get it. So what I am trying to say that even though you are expressing the running time something like this, so this many step count or this many basically step count is the fundamental operation, how many times it is repeating, right? So this many operations, you are still close to the reality only, you're not going away from the reality, but at the same time it is platform independent also. This is the type of benefit we are getting by doing this kind of an analysis. Now in the subsequent video we will see more about the step count analysis by taking small case studies. I will explain this so that you will get a very good feel about the step count analysis. Hope you get an idea. Thanks for watching. Anyway, it's some complex example also came in between in this video. Please leave that and focus on the remaining things. Okay. Anyway, that example which I taken, it will be very clear for you over time. So when you are exploring more into the subject, it will be very much clear to you. Yes. Thanks for watching. Doubts we will clear in our live class.